All right, everybody, we're going to bring it all together. We have our same enamine from before, and this time it's attacking an ester. When an enolate or an enamine attacks an ester, it's called a Claisen condensation. Lone pair on nitrogen kicks in the first step. Okay. Kicks in. Pi breaks and attacks the carbonyl of an ester. That's what's making this a Claisen. And then the lone pair of the ester comes back in the second step, which is blue. Comes back and kicks off this leaving group. And we generate this intermediate here, which looks identical to the thing drawn on the top of the screen already. So you think you're done, but you're not. The laws of pKa say you are not done. Here's your new bond. Here's an H that has a pKa close to 10. It's kind of like it's alpha to 2 carbonyls. Carbonyl here, iminium. In fact, if you put electrons on the nitrogen, that's a strong driving force. Maybe the pKa is less than 10 here. Doesn't matter. You've got a strong base. Something with a pKa remotely like 10 has to react. And you've generated this intermediate here. And there you go. And how do you make that into that? Well, we're going to take, well, we didn't generate that. I'm going to edit your question. We generated that. There you go. They're the same thing. I think I just do this. Please fix your product. You didn't have the one I drew. You have this one instead. There you go. First step, you're going to generate the thing I drew by mistake. Reminder here, this is going to be excess sulfuric acid. You just used up a whole mole of it right now in an acid-base reaction. It's gone. But if you have an excess, it's not gone. And seeing as we're doing a hydrolysis, I'm going to get to here too, where we have ethyl, and we also have OH on here. Where'd that OH come from? Step 2, water attacks. We're starting a hydrolysis right now. Neutralizes nitrogen. And there you go. And another reminder, here's the other side product. We did this mechanism already, previous video. I'm going to get from there all the way to the end somehow. Sorry? You forgot to remove this H from the water. Yeah, I never removed the second H from the water. Very correctly pointed out. You generated sulfate ion. Thank you. We need a third arrow, purple. neutralize the oxonium ion that you made with a blue arrow. Sorry about the blue crossing the purple. I think you see right through that, right? And there you go. Now it's got to be an elimination, and you're going to need to make 2 bonds to nitrogen using sulfuric acid. 2 bonds to hydrogen. First one is making it a better leaving group. Second one will be acid-base a little later. And oh, that's got red. We got lots of cool stuff going on here. OSO3H negative. Grab H. That's not red. It's blue. Make better leaving group. Make pi. This thing, as it leaves, becomes an amine. What's the most important thing about amines? They're bases. Please just know that next time I ask next week or Wednesday. It'll come up again. It's a base, and you got a reaction with sulfuric acid present. A lot of sulfuric acid present. There's a lot going on in this one little area here. Whoa. Nice. Not really. I'm going skinny arrow. You see that arrow? I don't think so. Yeah, I'm finally happy. And yeah. What we've generated here is a diketone, a beta diketone. And if I asked you to guess the pKa here, you should be able to give me a nice number. Nice. I had a couple 10s. Spoken in stereo. So, hey, KOET is a base. Pretty strong one at that. KOET. Definitely game to take that H off and generate an anion, carbon anions. That's when things start getting exciting. You gotta start thinking about synthesis. Start thinking about synthesis. There we go. This is where things get interesting. It's some new stuff. I don't know why. Please move this window. Okay. Your wish is granted. So what we have here is a nucleophile. And normally, what you've learned up until this day was that nucleophiles love attacking carbonyls. That does not change. This carbanion is attracted to the carbonyl. That's supposed to be slightly positive up there. Go with a, yeah. So it's going to attack that carbonyl maybe 1,000 times. Like attack and then unattack. What do I mean by that? It'll attack, generate an O minus, but there's something special about this nucleophile that means the O minus you just generated here will come back and regenerate the carbonyl and kick off the nucleophile. What kind of things do we kick off? What are they called? They're leaving groups. This nucleophile is also a good leaving group. Whoa. This is our first carbon nucleophile ever that we can say that. The nucleophile is also a good leaving group. We did definitions of leaving groups way back in chapter 9. And we said a good leaving group. Should we start with excellent leaving groups? Let's start at the top. An excellent leaving group is the conjugate base of one of the strong acids. Because when the strong acid was attached to H, that's when it was a strong acid. The H was attached to a leaving group that was in a strong acid. H leaving group, strong acid. Well, the leaving group's stable. That's why it was a strong acid. Okay? So good leaving group, H is attached to a leaving group, and the acid that before the H left had a pKa between 0 and 12. Conjugate base of an acid with a pKa between 0 and 12. And we just discussed that the pKa here was 10 to get to here. We didn't write it down, but I did. I wrote it down. Beta, that's the acid. There's the conjugate base. It's the conjugate base of an acid with a pKa of 10. It's on the screen, which means it's also a good leaving group, which means it can attack the carbonyl like we've done thousands of times. I'm exaggerating, I know. But every time we did it before, it attacked and you made an O-, and the O- couldn't come back down and kick off the leaving group because it wasn't a leaving group. Sorry, I was not angry. I was telling you why it couldn't be reversible. And in this case, it's going to be reversible. Ladies and gentlemen, clearly, if I attack the carbonyl, I don't get this, right? So yeah, that's happening, and then the leaving group's leaving. It's called reversible attack. But 1 out of every maybe 1,000 times it attacks somewhere else. This molecule, it's got some Greek stuff going on. If there's a pi bond between alpha and beta, and I want to remind you, we make alpha beta unsaturated carbonyls in Aldol Condensation. This molecule didn't just show up from nowhere today. We made it earlier today doing an Aldol condensation. We made this thing just now. We're bringing it together. And if you have a pi bond between alpha and beta, every once in a while, the nucleophile attacks like this. Because if you attack there, you can resonate all the way to the carbonyl and generate a stable enolate intermediate. This is called a 1,4 attack. I better put it in purple. A 1,4 attack. Where the heck does that name come from? I'm going to put some numbers on the molecule being attacked, and the numbers go like this. The atom that gets attacked is going to be labeled number 1, and count all the way to where the electrons end. They didn't end at 2. They didn't end at 3. They ended at 4. Called a 1,4 attack. Is a version of the title of 19.2b. No, not even 19. Yeah, 19.2b is a version of conjugate addition. Conjugate is just a fancy way of saying there's resonance involved. And there clearly was resonance involved after the attack, right? Okay. And this one generates a intermediate that looks like this. Exciting stuff there. That's an enolate, which is the conjugate base of an aldehyde. How do we get there? What's my best acid around? And once again, HOET. I don't have to draw it because I had it for you this time. ETOH is over that same arrow. It's right here. HOET. Acid base. 16 goes to 20. End of story. pK 16 goes to pKa 20. Then we're going to leave it there for today and do the mechanism here at the start of Wednesday. I'll edit in our activity 1 Wednesday. We'll start with this little baby here. And I'm going to give you credit because everybody in the room right now was here for activity 4. You're already getting credit for activity 5. So right today, so you get to take this home with you. And I didn't need to do this on the video. I'm sorry. And here we go. Bye-bye.